Hello everyone, welcome back. In this particular video, we're going to talk about the elimination-addition reaction of aromatic compounds. Now, this reaction is sort of a follow-up to the nucleophilic aromatic substitution reaction. So if you haven't watched that video yet, I would encourage you to please go ahead and watch that video. But to get started, let's look at some reaction here. Now, we know that for a nucleophilic aromatic substitution reaction, there must be a strongly electron withdrawing group present in your aromatic compound. And this electron withdrawing group should be ortho or para to the leaving group, or it can be ortho and para. It does not have to be just one electron withdrawing group, but what you need is at least one electron withdrawing group. So if we use a simple aromatic compound like chlorobenzene and react it with a strong nucleophile like sodium hydroxide, we will not get any reaction because there isn't an electron withdrawing group present in that ring. But in fact, if we do this reaction at high temperatures and pressures, so the temperatures are like significantly higher, so like around 300 degrees Celsius or so, we, in fact, observe a reaction. So the chlorobenzene is converted into the phenol. So this is chlorobenzene. And our product is phenol. So if you look at it overall, our leaving group here was substituted with the nucleophile to give us the product, okay? Because this hydroxide here is the nucleophile under these conditions. So there is a substitution reaction that happened, and you will get the chloride out at that point. Now, there are other examples where the reaction does not have to be heated this high. So for example, when you take chlorobenzene, and if you react it with sodium amide, as a nucleophile. This reaction can be done in liquid ammonia, which is like low temperatures essentially. So you can do the reaction and you can again substitute this leaving group with the incoming nucleophile to make aniline. So you can start from chlorobenzene and you're able to make aniline here. But what's peculiar about this reaction is that there isn't a need for this strongly electron withdrawing group, but it does need some forcing conditions here. So we're using like really strong bases. Some reactions require high temperatures, some can be done at low temperatures. So an interesting characteristic of this reaction is revealed when we consider the reaction of substituted halobenzene derivatives. For example, if we look at the reaction of parachlorotoluene with sodium amide under liquid ammonia conditions, we would expect one product here, which would be the para-aminotoluene, where the NH2 group substitutes for the chlorine. So this is the product that we would expect. But it turns out under these conditions, an additional product is formed, which has the NH2 group meta to this methyl group, or at a different carbon than where the chlorine or the leaving group was located here. So the mechanism of this reaction must now explain this observation that we have where we are able to make two different products. And again, as a comparison to the nucleophilic aromatic substitution reaction, notice that we do not have an electron withdrawing group here. The methyl group is an electron donating group. It's weakly activating. So it is not like a nitro group that we've seen in the nucleophilic aromatic substitution reaction, which was electron withdrawing. So to explain the formation of both these products, scientists had to come up with a very innovative mechanism that involves a very weird looking intermediate. And this is a very high energy intermediate. So what they suggested is that the first step in the mechanism involves the deprotonation of an orthohydrogen by the base in this reaction. So when we consider the leaving group here, there are two possible orthohydrogens for this particular molecule. So in the first step, what happens is that the base deprotonates one of these orthohydrogens. Doesn't matter which one it deprotonates. They're both equivalent here because it is a symmetrical molecule. So as the base deprotonates that hydrogen, the electron pair in this bond falls into the space between the two carbons here, and the chlorine group is kicked out. Now, this electron push might resemble something that we see in E2. So I would say this is the electron push here is similar to what we see in an E2 reaction. So we can treat this as our alpha carbon. This is the beta carbon. So what we're doing is a beta hydride elimination over here, sort of. Okay, so the beta hydrogen is eliminated, and at the same time, the leaving group leaves. So we deprotonate the beta hydrogen. And so now if we look at it, what this is going to yield us or lead us to is this intermediate where we have a triple bond in an aromatic ring. This intermediate, now not this specific intermediate, but an intermediate like this, which has a triple bond here, is referred to as a benzyne to account for this triple bond that is present in this molecule. Now, realize that this is a very unstable intermediate. This should be highly unstable because the geometry here just doesn't allow for this triple bond, because these carbons are part of a ring, and now these are sp hybridized. So that means the hybridization really doesn't work over here. Okay, and the geometry is not allowed because those carbons would like to be linear in geometry. So this is a very high energy, unstable intermediate. But the formation of this intermediate explains how we get these two products. Because once we get this high energy intermediate, in principle now, in the next step, what can happen is that the amide, another molecule of this nucleophile, can attack either one of these carbon atoms. So these carbons can be attacked by the amide nucleophile. So it can go and attack the position where the chlorine was originally located, and that's going to push away this electron pair to the adjacent carbon atom, and that's going to give us an NH2 at the position that's para to the methyl group, and a nucleophile or a base at the adjacent carbon atom. So it's going to give us a negative charge at the adjacent carbon atom. And then subsequently, this negative charge can get protonated using ammonia, like a hydrogen from ammonia. It can abstract a hydrogen from ammonia to get protonated and give us the product that we have here. So NH2, so the hydrogen is put over there and the methyl group is here. So we notice that we made this para product here. So this is the para product. We've got that, and this one is the meta product. So we've made the para product over there. Now, the other possibility here is that the amide, attacks the meta carbon here. And if that happens, and meta with respect to the methyl group, that's what we are referring to. That's our reference point here. So the meta carbon can be attacked. And if the meta carbon is attacked by the amide group, then this triple bond is going to move in the opposite direction. It will put the negative charge on the para carbon. So that's going to bring us to an intermediate where the NH2 is connected to the meta carbon, and the negative charge is now on that para carbon. And very similar to the para product, this intermediate can now get protonated by ammonia, or can abstract a proton from the solvent ammonia to give us the meta product. So methyl group over here, NH2, and the hydrogen. So that way, the benzyne intermediate allows us to explain the formation of the para product and the meta product that we see in this reaction. So the formation of such a benzyne type intermediate in this reaction can be confirmed by indirect methods. One possibility is to do a Diels-Alder reaction on this benzyne intermediate, and then you can trap the benzyne intermediate into a product and analyze the product to see if there was a benzyne intermediate present. So that's the mechanism of an elimination-addition reaction. Unlike the nucleophilic aromatic substitution reaction, what clearly differentiates this reaction is the absence of an electron withdrawing group. So what we have here is an electron donating group and the possibility of two isomeric products under these conditions. I hope you find this discussion helpful. Bye.